Hi, this is Chris Kiefer, and welcome to the Power of ERDC podcast. Today, we are exploring how ERDC combines its deep historic expertise in materials like concrete with cutting-edge insights into newer substances like polymers to develop and characterize advanced materials with unique properties for various military and civil works applications. Joining us is Dr. Travis Thornell, a research physical scientist at ERDC's Geotechnical and Structures Laboratory, or GSL. Travis, it's good to have you.
Great to be here, Chris.
Yeah, and we also have Dane Wedgeworth, a research physical scientist at GSL. Dane, welcome to the podcast.
Thanks for having us.
Absolutely. So I want to talk about maybe kind of even something unique about each of you. You both have degrees in polymer science, and you came to ERDC at a time when ERDC didn't have many researchers in that field. Kind of how have you seen ERDC's polymer science expertise grow over the past decade?
So I started as a research physical scientist back in 2018. At the same time, Dane was a student intern during his undergrad year. So it's been fun to kind of grow with him.
Yeah.
And I came in with my PhD in materials engineering. So it was really great to kind of see things blossom over the almost 8 years where we've kind of used polymers in a variety of different applications from basic to applied research.
Mm-hmm.
Yeah, we've just been, when we both started, able to advance things pretty significantly, and being able to contribute to that has been awesome as far as growing our characterization equipment and techniques, and being able to provide a lot of that has really been stood up and, since we both started. And I think it's exciting to see how things have transitioned more from off-the-shelf type material systems to more materials by design. So that's been kind of our focus in how we approach projects that we have.
Sure. So talk about, again, kind of at the same time as your career has grown, just ERDC's expertise and knowledge in polymers and polymer science has grown, and you all, I guess, being on the leading edge of that in a lot of ways, bringing that new expertise. And it's gone from what you all, I know you told me this the other day, when y'all were hired, there were maybe one or two other people here, and how many did you say there are now?
Yeah, we're kind of
Polymers?
getting close to about 20 people
Yeah.
across the organization, across all the labs, doing kind of polymer chemistry, polymer engineering research, be it from wet chemistry to more polymer fiber reinforced composites. So that's really getting into a bunch of different research areas that are across the organization.
And why is that significant, seeing ERDC's polymer expertise grow over the last decade?
Yeah, I think it's a lot in terms of what we see different needs are that are coming out from our different collaborators and partners, and being able to approach that with a unique mind to say, maybe we don't have to use traditional materials like concrete and steel. Maybe we can start incorporating some novel material development. And so that's been kind of our forte, is stepping into those roles and saying, hey, what can we do with different types of materials that are on that cutting edge of research, and apply those to these different problems that we have.
Sure. And that builds on a long expertise. ERDC, again, almost been around when you go back to the Waterways Experiment Station here in Vicksburg, almost a century, following the Great Mississippi River Flood in 1927. And so it kind of all started studying levees and led to concrete expertise, airfill pavements during World War II and so forth. So ERDC's got this deep expertise in concrete. And I guess that was maybe the original materials expertise. How does looking at newer substances like polymers kind of build on that historic expertise and supplement that historic expertise?
So, I think it's important to understand all of the application spaces of polymers. And, we think of it maybe as plastic. You have your traditional polymer types with milk jugs and plastic bags. And so opening that up to all the different application spaces. So we have historically with airfield matting and expeditionary airfield matting, being able to look at coatings on the surface for anti-skid and resistance. And so a coating, a paint, polymers are used extensively in those as far as the matrix of the material. And so transitioning that into other areas as well, you have, ballistic and blast protective panels, polymer composites. So it's really expanding the horizon to say, well, it's not just plastic. We can think of it in terms of what applications it's used for. And I think that's the important understanding there, is bridging that gap from, okay, we know it's used in certain commodity areas, but it's also used from the military side and even the civil works side as well.
Sure.
In the similar heritage of concrete across ERDC waterways, last summer we had a chance to do a tour, and Dr. Paul Malacher, who held various levels of leadership positions, technical director, he looked at us and he's like, when they were kind of renaming parts of the organization, he fought to add and materials into certain things, and being in the concrete materials branch, even though it specifically says concrete, we've been doing a lot in materials, and that was kind of like a cool moment to hear that, someone with a lot of future looking perspective, like we'll need to invest in material science as a whole and not just be in infrastructure of
Yeah.
concrete. And we still are able to do work with polymers and concrete as well today.
Yeah.
Tell us more. I kind of want to peel back the onion a little bit more on polymers and the significance and research. When you talk about materials, that I guess goes broader than polymers too. I mean, kind of tell us what that and materials you just mentioned, what all that kind of encompasses, and maybe even why that matters.
So just kind of on the link scale of like science and engineering, when we're thinking about materials, we're going like what makes up the material on the atomistic scale. And so I like to think of that when we're talking about polymers, I envision almost the structure of how carbon's connected to other carbons and other elements. And the same for metals and ceramics, how they're in the lattice. And really that dictates all of the end use properties. And so between all those different materials and combinations that lead to composites, that's where all these properties are coming from and how processing to get our final form of a material. So it's really kind of understanding all the different link scales of a material.
Sure. Ultimately, it's about finding different properties, unique properties, special properties, for various applications.
Yeah, not all materials created equally. So you can't just concrete or use a certain metal. You're going to have to use whatever is needed for the certain application or solving your problem. And that goes from polymers. Different structure of the polymer gives it different characteristics. They can withstand different temperatures based on what it makes up with. If it changes from more ring structures, might have higher thermal stabilities, or if you have longer chains, may give you more flexible, kind of like a rubber-like feel to it.
So yeah, I guess I kind of want to ask, and you've spoken to it a little bit, but to even build on, like, why is ERDC interested in polymers? What makes them unique? Why is it special to be having this expertise in polymer science?
Yeah, I think it really starts with what are our biggest challenges, kind of the grand challenges of the different work that we're involved in, looking into, is this the best material suited for the job, or can we start to prod at different areas? If we're talking about lightweighting, polymers are an excellent way to decrease the weight of the material. If you're talking about just the condition that it's being put in, if it's highly corrosive environments, salt water, things like that, you're not going to have the same corrosion as you would with metals. And so you're even thinking about what's in the concrete. There's a lot of reinforcement metal material in there that can corrode over time. So you're thinking about increasing the lifespan of the material, which decreases your costs as far as maintenance and upkeep. So those are, obviously some things that come to my mind as far as, why polymers are unique in terms of the organization and what areas they fit into. But you just have so much tunability and control over the polymer structure and how that affects its final performance. So I mentioned, milk jug, we're taking it from that scale, same type of carbon and hydrogen. You're changing the length of these chains, and now you have something that it can stop projectiles. So with the same material, you have the ability to tune those properties, and that's very unique as far as materials go.
Sure. We talk about, again, going back to say a decade, if you kind of look again, bench of your career and kind of how much it's grown, what have been some of the biggest success stories over the last decade at ERDC in terms of polymer science research?
We've had a lot of great collaboration with the University of Southern Mississippi, looking at polymer composites for military engineering. And some of that was looking at ways to replace metal parts on very heavy modular systems. And so one big success was looking at ways to lightweight the modular protective system, or the expedient, the EREB system. And so there's some large metal parts that hold the panels together.
And either, just to back you up, sorry, but for people to understand, this is for protect warfighters in the field, dining hall facilities, for instance, and so forth. Protection from mortars and such. Modular panels that you can set up. And anyway, I'll let you go from there.
Yeah. So very modular system. So any ways that we can cut down weight, but also the existing metal Z-bar that held this complex geometry would actually deform pretty rapidly and have kind of elastic failure. Whereas if we started looking at ways to make polymer fiber composites that we could thermoform into that geometry, that could withstand multiple hits, but also hold its shape in near failure modes. So that was really a big win for us early on.
Yeah, and we talk a lot about these polymer properties where Travis mentioned maybe some of these ring structures that can give rigidity to the system. We tend to think of it in two classes, thermoset and thermoplastic. So one being a rigid network type structure of fishnet, if you will, where each of these points are connected, rather than more of a bowl of spaghetti. So you have these individual chains that can move around as in the thermoplastic form.
Okay.
And so, being able to utilize with these composite Z-bars a thermoplastic resin instead of the thermoset rigid non-reprocessable resin, it opens up some different avenues to, if there was some sort of failure, we could just heat it back up and reform it. So you have the ability to reprocess and reuse. So there's less waste involved as well, with similar performance to your traditional systems.
Yeah, sure. To back up a little bit at a high level too, I mean, when we talk about polymers, when we kind of talk about polymer research and so forth, I mean, for the audience that's unfamiliar, I mean, what exactly are we talking about when we're talking about looking at polymers?
So about 100 years ago, most people would consider polymers the goop and really dirty science.
Yeah.
It was just kind of what was left over in the flask. So over time, it's really gained, kind of the plastic industry's really gone up. And so being able to build up different structures. And so when we're talking about polymers, and there's kind of a repeat unit, and that gives us what we think of the structure. So polyethylene, or ethylene unit, and poly being many. So many ethylene units kind of giving us that and correlating that structure all the way to their properties. But it used to be this kind of dirty goop that then's kind of morphed into its own thing of sophisticated, multidisciplinary, not just chemistry, but there's all types of materials, mechanical engineers, chemical engineering, all into that, kind of using different aspects.
And again, the advantage of studying it for civil works applications, military applications, is certain properties that you want or certain properties that you don't want that you can engineer around. Correct.
Yeah. So polymers, we can make them in a thin films, thinner than what you would think as a paint, but we also make them as paints. And then going up to very bulk level, big units like a panel or some type of overlay. So various polymers perform differently in both of those, but they're very tunable across the length, scale, and size of that material.
Sure. What are some of the unique challenges of polymer research?
Yeah, so there with any type of material, you have to consider the cost to utilizing them, and there's a lot of specialized research that goes into it. So if you don't necessarily need a Kevlar material, maybe you step down to a different class. So there's costs associated with all of these things, but in terms of what are the challenges that we're trying to overcome in different environments, there is a UV degradation effect in the sun. So we're talking about traditional thermoset type composite panels. There's some susceptibility in these kind of sunlight conditions. So we try to overcome that by addition or changing that matrix material type. And so there's some resins that are less susceptible to that damage. And so just associating what are the costs of that application versus the benefits. And so I think that's one for sure, and just the environmental stability aspect. And there's a second being, you don't think of the polymer as strong as steel. Obviously, it's different application, but there's a process called creep, whereby under certain loading conditions, you might see some deflection and change in terms of how it holds up to that load. So adding in different functional additives, different carbon fillers, you're looking to increase that creep resistance and hold your properties more. So associating those environmental effects as well as your material toughness, those are kind of what our challenges and we're trying to overcome.
Sure.
Yeah.
Do you have anything else to?
I think
Yeah,
Dane covered
yeah.
a good bit of it. I mean, I think there's a lot going on with polymers. Being able to get the right quantity of polymers. Because a lot of the strength is on how long you can make the chains. And so if you have some process that shortens your chains, that can be a degradation of properties. And also like replacement of across materials, polymers will behave under different thermal loads. So they might swell or get larger, whereas concrete maybe doesn't have as large of a thermal expansion.
Sure.
So there's different things that engineers are tracking and modeling in, as well as in use to overcome some of those kind of drop-in challenges that are larger adoption. So
Tell us, and again, we've kind of talked about the history and some of the big advancements over the past decade, but kind of today, what does ERDC's materials research look like? Kind of what sort of projects are you working on, and kind of what is the scope of it?
well, if anyone has a chance to ever come tour our building specifically, at the front, we have a nice wet chemistry lab. So you can do a lot of polymer synthesis that has characterization right next door. And as you go through our building, you kind of go through the different link scales of polymer science and processing. So then we can go to more extrusion based and higher levels. So that's really neat to have just in-house with our branch. But across our different laboratories of different capabilities that we're kind of leveraging across. So we do a lot with the environmental lab that has different characterization capabilities and processing. So that really sets us up to really do a lot of fun things in the space across from basic and applied research. We do a lot on the basic side, very active in our basic research 6-1 program of trying to understand fundamental aspects of polymer science, either kind of understanding how polymer networks or thermosets are formed over time with different additives or under different loads, as well as trying to understand how we can control material deformation and degradation. If we understand how a material breaks apart, if there are loose links in a material, we can control that to our advantage.
Sure.
Yeah, as far as our interest broader level, we're interested in how different impacts energies affect our systems. And so you have the ability to control the material properties from a gel-like substance to a very rigid material. And so you're spanning, 5 orders of magnitude in terms of its stiffness and modulus. And so, we're investigating how we can make these different systems, how energy is affected, how we could layer these into different structures, how we can look at different functional additives like carbons, and understand how we can process it differently through extrusion-based methods, through solvent film casting methods, as well as 3D printing. So it's a broad range of interest, but we have the capabilities to control those properties and scale it throughout for the different applications of interest.
And another big area that we've talked all about, kind of like experimental things, we leverage a lot on the computational chemistry side. So going all the way up from density functional theory, atomistic modeling to finite elements. So all different types of polymer scientists working in that, working with us, either us feeding things in their model to try to predict what material might be the best for energy absorption shockwave, to they already have an existing model that they want to build and see what they can project back to us. So it's like kind of a great for our organization to have both that crosstalk and one, location.
Yeah, I wanted to ask about that. I mean, we like to talk a lot about, because I think it's one of the things that makes ERDC unique is this cross-laboratory collaboration. In fact, I guess we had a podcast a couple episodes back about the RD26 workshop,
Mhm.
or a bunch of our recent episodes, we're kind of filmed on location. Some of our listeners may have seen those. But what we're kind of talking about is that workshop's ability to bring together researchers from different disciplines, different laboratories, all working together. This is, I guess, an area where that's happening a lot. You all are both at GSL, but you kind of indicate a little bit ago that you're working with the environmental laboratory, for instance. But I'd imagine you're also probably working with, I know, other branches at GSL, as well as other laboratories as well. Kind of just talk about how much this research is benefiting from that cross-laboratory collaboration.
Yeah, a lot of our stuff is leveraging the military engineering research area, and that's kind of where our sweet spot is. But we have so many characterization capabilities as well as synthesis to be across everything. So I actually have kind of done a lot more work in synthetic biology. And so me, with some of those guys from our construction engineering research lab that are doing all types of fun things with the bacteria and kind of green chemistry has been kind of fun, and showing them like, okay, here's what I've been talking about. So it was great to have them one side, but we're working across. We're doing some in the IOE research area,
Installations, operational environments. Yeah.
and then going to some of the civil work stuff. So we're kind of very well diverse, either leading projects or supporting. So that's been kind of fun, even supporting, picking up the phone and being like, hey, is there a way that you can test this? Like, actually, yeah, we do have a specialized fixture, or it's a different translation. Like, oh, we would call it this way in our discipline, and going from there.
I think we talked previously too. ERDC obviously does a lot of modeling, and that you all are often informing models on, and you kind of even mentioned it a little bit earlier, but updating, maybe making sure a model's more accurate based on something that you found from your materials research or from a basic research project or whatnot. I mean, that's happening a lot too. I get the impression, correct?
Yeah, for sure. I mean, Travis and I both have ongoing research projects that are heavily influenced by this information circle, if you will. So we're providing them insight, they're providing us insight, and we're keeping this as a continuous evolution of the material model as well as our experimental setup. So it's been very beneficial to us, and it saves a lot of time in the lab as well. If you're not doing 20 reactions, you could cut it down with the computational time to just a few high impact ones. So that's really where we've seen a lot of effect. And when we sit down with them and we show them, this is the information we're getting from our testing equipment, let's try to figure out what's happening. You're just seeing atoms on the screen, I'm seeing actual material. How do we blend that together? And I think that's something that we're very interested in, and it's been beneficial to ERDC and the organization as well. So
yeah, I can imagine. Talking about some specific projects that each been involved with, and let's start, Dane. I knew you were just involved with a project in 3D printing you mentioned earlier. I know that's a big part of what you all do too, and different materials related to 3D printing. But you came up with a project to help 3D print a material that can be useful for electronics. To tell us more about that.
Yeah, and I mentioned a lot of our functional additive work. One recent area involving my long-term training that I was working with Virginia Tech on. Did a lot of research up there and on liquid metal. So this is a room temperature liquid composite material of gallium and indium combined together, and it's a safe mercury, if you will. So this is a physical state, so it looks a lot like that. And so we're able to incorporate that into our polymer matrix to make these functional additives for capacitors, resistors, this type of work. So in soft electronics, so we have a soft matrix material like a rubber, and we incorporate this functional filler. And so we're trying to be able to utilize traditional reprocessable thermoplastic networks, which historically has been more on the non-reprocessable side, and investigate the use of 3D printing to unlock some different structures that we aren't able to do with traditional casting. And so this project has been a real collaborative effort. A lot of the computational modeling has contributed to that. Understanding these liquid metal oxide layers that form on the surface and how that influences our mechanical, thermal, and electrical properties. And so it's really been a good effort as far as advancing that understanding and being able to utilize this for those applications in electronics.
Sure. It's fascinating when you talk about I know we're just kind of scratching the surface
Sure.
in this discussion, but I mean,
Yeah.
kind of the kind of things, liquid metals and so forth, that I think, a lot of people can't even imagine that you all are really looking into, which is
Yeah.
awesome. Another thing on those lines, again, people probably don't think about in their day-to-day life, that I know you're working on, Travis, a project that you just worked on, make sure I say it correctly, with a polymer material capable of visualizing shockwaves. Tell us about that.
Yeah, so that was a great project we had that we leveraged our collaboration, our ongoing collaboration with Southern Miss, as well as researchers at Arizona State and NIST, National Institute of Standards and Technology,
Mm-hmm.
where we were incorporating mechanophores into polymer networks. And these mechanophores are points that we can add into the polymer chain that when they break, they can kind of fluoresce or kind of have a color change. So when we kind of started that, we were thinking kind of more sensing of damage.
Right.
And we had some work previously with some modeling on how thin films of materials based on the type of polymers would behave differently under different ballistic rates. So some polymers may break apart and others might just kind of unravel. And so we
Sure.
wanted to understand, like, okay, we know that these mechanophores, when they break, will have kind of a visual cue of what happens. And so working with NIST, they have some specialized techniques that would kind of mimic a ballistic test, but at a very like nanometer, sub-micron level thin film.
Yeah.
And so we're able to look at that, and based on the type of polymer characteristics, how it might absorb energy, but then using kind of some visual observations of the fluorescence spectroscopy, you could see how the literal like impact of the projectile, this little small silica, would go through. And so we're looking at it from the military perspective, but the larger science community thought this might be a great way to visualize like Mach cones for kind of space travel. So it was interesting, but like for us, very much applied research going into understanding ballistics, but then the science community, high level journal was looking at this and kind of being like, oh, this might be a way to visualize this. So that was really neat to be a part of.
Yeah, fascinating. I guess especially when you get into basic research, you do a lot of basic research, you never know where it will lead and all the applications that'll come from it. Characterizing materials, I know, is another big thing, and kind of just talk about just the expertise in that, and kind of some of the ways you've applied it and significance and so forth.
You want to start, Travis?
Yeah. So when we've got many ways to test materials across from our labs, and it goes from structural to thermal to mechanical. So there's kind of the three biggest areas. My specialty is in polymer rheology, and that's the $100 Jeopardy word for the study of flow and deformation. So it's a lot easier when we're talking about mechanical testing of a solid. We can stretch it, do a tensile test, or compress it. But for softer materials or liquids, you really can't clamp that. So we look at shear. And so basically this is a measurement of shear that we can use. And so I did all my PhD work in rheology. And so it has kind of far-reaching applications or implications towards understanding the structural materials, but also how you might process it. So we can mimic what would happen in an extrusion process or how you might be applying the material. So we have some projects looking at paints. And so we can understand how you might apply, at what speed do you need to apply the paint? What's it going to look like, and tie that in with observations. But we can also use it as a way to probe a material's viscoelasticity. And so there's the fun word that a polymer and different materials can behave both like a liquid and a solid. And so we can use this instrument to understand at certain points, at certain deformations and times, does it behave more like a solid or a liquid? And so kind of a characteristic of what would siliputty do. So if you pull on it really fast, it breaks. You pull on it really slow, it stretches.
Right.
So basically, I can measure that. And for different materials, that means different things for their applications and what time scales you can use them for.
Yeah.
And then, as following along to that with our thermal testing, we're really interested in different thermal transitions that happen within polymer materials. And so, unlike metals, at operating temperatures that we would see on Earth, you're not going to have a metal melt. And so with polymers, though, there's could be some situations where you're maybe not quite melting, but you're in a position where you're transitioning from a glassy-like state to a rubbery-like state with the same material. And so you really want to understand that when you're applying it to something where you need mechanical robustness, you need strength. And so you need to be careful. Is this going to have any conditions where I would be going outside of that range, think about it in cold conditions as well. So
Sure.
we do a lot of work with the Cold Regions Research Lab as well, and understanding, what is this material going to behave like negative degrees? And so that's important for polymers. And so these thermal analysis techniques that we have and equipment are very vital to understanding that. Very standard what we would do if we had a new material project where someone would be interested in what are these behaviors. First thing we would look at is kind of the thermal degradation. So how stable is it? To what temperature does it go before it burns up? And so that's important. If there's any kind of additives within the material, we can understand how much, what does that loading look like? If we see good performance out of one sample but not the other, maybe we can determine, oh, well, there's a little bit more of this additive, and now we can understand that's the reality. So from the thermal standpoint, that's very key in a lot of the work we do. And then mechanical, like Travis was saying, we really are looking at solid like samples and understanding this kind of time and temperature effect on the sample, to where maybe given sufficient time, that sample could have some behavior that you don't is not desirable. But then also, given sufficient temperature, can you cause those same reactions? So those two are hand in hand in terms of mechanical properties as well.
Yeah, sure. What makes ERDC unique in terms of, I mean, a lot of other places are looking at polymers and polymer science. What makes the polymer expertise at ERDC unique?
I think we're able to kind of handle problems across different length scales of materials. So we can make it from like the nanometer, atom to atom, building it up, to then being able to transition it to large panels, but also supplement with kind of the modeling as well. So we have, within our organization, we can do just a little bit of everything in that area.
Yeah, and our purview as far as our application-driven research is very unique into our organization. And so we're thinking about how we can apply this material, for example, to stop a projectile, but also, how could it be used in our civil works infrastructure?
Sure.
So, it's not necessarily the same application by any means, but the material is the same. So I think we're positioned uniquely in that way, in which we have very unique applications. We have very unique facilities that are world-class here as far as our projectile testing, blast testing, and all of our polymer equipment, characterization. When you think about things like microscopy and understanding an atomistic kind of level, what's happening, we all have that in one building. So it's very unique as far as ERDC and how we're positioned within the structure.
Yeah, sure. A lot of partnerships as well. I mean, you already mentioned some of them: Virginia Tech, Southern Mississippi, Arizona State, I think it's talked about before. Or are there kind of other, talk about just some of the partnerships that you all have?
Yeah, we have several, probably too numerous to name all of them as far as academic partners, but that's really a great way that we can connect with students and understand, what type of research is on that cutting edge, because we're really interested in bridging the gap between the cutting edge, what's practical and what's useful for our organization. We also have a lot of government partners as well, Army Research Office, and we're looking at what are they funding in terms of their polymer program, attending some of those reviews and being able to understand these collaborations with multi-universities, and those types of collaborations help guide our research in terms of where we're looking. But
Yeah, so just echoing what Dane said on a lot of that with those partnerships, and we're pulling our weight just alongside of them, leveraging their expertise and our expertise, especially on the government side. Like, not so anyone in the government's doing the same type of research, that at least, okay, everyone's aware, okay, they're doing this type, we can do something similar. Here's the lessons learned. And so there's been a lot of great crosstalk with that, and as well with our university sponsors. We're also doing work with some industry and government contractors, and really, we've mentioned it a few times with graphene and carbon nanotubes from different sustainable or U.S. sustainable localized sources. So there's some key relationships that we built over the years.
Yeah, strategic partnerships in those different areas that help guide our research, but also facilitate, novel testing technologies like NIST and their projectile testing. We can leverage that and our partnerships and have a lot of good collaborative research and leading to publications and leading to bringing on new people to our organization through these university partnerships as well. So that's really been our bread and butter in trying to understand how we can exist in that same network where everybody might have a polymer team, but we're all talking together to achieve our similar goals.
Sure. Yeah, sure. Last question for each of you. This is such a cutting edge field, but looking at kind of, it's always changing, always developing, kind of what's on the horizon in terms of that you all are most excited about in terms of polymer science research?
So I'll go first. I think, I mentioned utilizing thermoplastics and thermosets. So, there's been a lot of unique work in that field of we want the properties of the thermoset to where it's very mechanically robust, but it's not reprocessable. So how can we bridge that gap? And so this, novel class of materials called vitrimers or these dynamic networks to where we can leverage that same technology that is giving us these mechanically strong materials alongside the reprocessability. If we go over a certain temperature, we can remanufacture them. And so coupling that with our functional additives, being able to achieve unique architectures. 3D printing is obviously an area to where you cannot get traditional cast parts the same way you can. I think is really what's on the horizon as far as advancing some of that technology and what I'm most excited about.
Yeah, those are some great areas. I'm really excited about continuing to look at kind of how polymers can absorb energy across the length scales. So we're doing a lot with polymer composite panels with different additives and functional layers. But also we're doing a lot on kind of the small scale. So a team led by researchers at the Environmental Lab, ITL, and GSL were recently awarded the 2025 USACE Innovation of the Year of very thin films that could absorb a wide range of energies for protecting the warfighter. So really trying to understand how much further we can go with different structures and how we can process that to then transition at higher levels.
Yeah, sure. Well, thanks. Very fascinating and appreciate you all taking the time to discuss work that's really on the cutting edge. So thanks. Thanks for joining us. Thanks for all the work you do, on behalf of the nation and the warfighter and just all the solutions you guys are coming up with. So appreciate it.
Thanks, Chris.
Yeah, appreciate having y'all.
Thank you, Chris.
Yeah, for sure. And for our audience, again, thank you for joining us today. We remind you, there are more resources available on our website, poweroferdicpodcast.org. You can find the video of today's interview, the audio form of today's interview, as well as various resources and more information about ERDC's materials research and polymer research. So we encourage you to go there. Reminder, you can look for us every Tuesday at 10 o'clock. We've got a new episode. You can find it on our LinkedIn channel, on our YouTube page, as well as on the website, poweroferdicpodcast.org. So again, that's all we have for today, and we will see you next time.